Hi everyone, you all must have seen videos in which astronauts in spaceships are floating and it seems like they don't feel gravity like we feel on Earth. In a smaller scale, you must also have experienced while going in a giant wheel. As you come down, you feel like you have lost weight, you feel like you are not being supported, right? That feeling, that sensation of losing weight is what we call in physics weightlessness, and today's video is about weightlessness. In physics, the weight of a body is given by the mass of the body times the acceleration due to gravity. Now, this value depends on the planet where you are. So, for example, near Earth, if you drop something, you see it falls with an acceleration of 10 meters per second square approximately. So, therefore, we know the value of this near Earth and we know the mass of the body. So, we can easily calculate the weight of the body using this formula. Now, whether you are in a giant wheel coming down or whether you are an astronaut in a satellite, in both the cases you are under some gravity and you have mass. So if both are not zero, how can the weight be zero? Why are we calling it weightlessness? Let's try to understand that. Now consider a situation where you are standing on a weighing scale and the whole system is at rest. Okay? Now, there are two forces acting on you. One is your weight, which is the gravitational force, and the other is the pressing force between you and the surface of the weighing scale, which we have discussed many times in our previous videos, right? Okay. So let us draw the two forces. So one force is the gravitational force which acts downwards, which we call the weight, and the other is the pressing force, right? So your body, or I can say your shoes, are pressing the surface of the weighing scale downwards. Yes or no? So you are pressing the weighing scale downward. Therefore, the reaction of this will act on you upward. And that is what we call Newton's third law. So if this is N, this also will be N because action and reaction are equal in magnitude, remember. Only thing is they are opposite in direction. Now, since he is at rest, his acceleration would be equal to 0. If you apply Newton's law to this body, it says the total force on a body is equals to mass times acceleration. Now what is the total force on this person? One is weight downward and one is normal force upward. So the total will be W minus N. Why minus? Because they are in opposite direction, and that would be equal to mass times 0, which will give you 0 on the right side. And therefore, if you take normal force this side, you will get normal force equals to W. Now, observe this carefully. The force which we calculated here, the normal force which is on you by the weighing scale, is also the force on the weighing scale by you, remember. Therefore, since this is the force which actually acts on the weighing scale, this is the force which actually pushes the spring inside. And therefore, this is the force which deflects the needle in the weighing scale. And thus, it is this force which is measured by the weighing scale as your weight. It's not your actual weight which is being measured. It is the normal force which is getting measured. However, when your system is at rest, you can see the weight which is measured, the one that we call normal force, is equal to your actual weight. So we don't have a problem here. Now next we keep everything same except we allow the system to fall freely. When I say the system is falling freely, what does it mean? It means the system is not getting any support from any other body. The only force pulling it down is gravity. When a body is falling freely, its acceleration will now be no longer zero. Obviously, it is no longer at rest. So its acceleration is equal to acceleration due to gravity, which we write as g. So now when you apply Newton's law, this a you cannot substitute as 0. It has to be g. Right? Now, The weight of your body already we have seen before is mg. Minus n here is equal to mg. So therefore your n becomes equal to, if I bring this mg this side and minus n that side, I will get mg minus mg, which will come out to be 0. What this result means? This result means that there is no pressing between you and the floor. It's no pressing. Now, do you need so much of maths to understand this? No, because since the system is falling freely, my shoes and the surface of the weighing scale both are falling together at the same rate, and thus I am not able to press the weighing scale. And since I am not able to press the weighing scale, the normal force is 0. And thus, if normal force is 0, the spring inside is also not getting pressed. That means the reading shown by the weighing scale will be also 0. You, on the other hand, since you don't feel this normal force, you don't feel like you are being supported, and therefore you get this sensation of weightlessness. So please remember, weightlessness does not mean your actual weight has become 0. Your actual weight is mg. However, the weight which is measured by the weighing scale, or the weight which your sensation gives you, the feeling of your weight, which is the normal force, that becomes 0. If you check the thumbnail of this video, you will see Stephen Hawking floating and feeling weightlessness. What they did is they took him and other people in an aeroplane, and the aeroplane was made to fall freely for some interval of time. During that interval of time, as we have seen, the normal force becomes 0, the pressing force is 0, so there is no contact, so everything seems to float, right? To show you guys a demonstration on weightlessness, I took a container with a hole. First, I keep the container at rest, and since there is a hole, the water will be pulled by gravity and it will come out with acceleration equal to g, right? However, if I allow the container to fall freely, okay, if I let it go, then you see the water here, which was supposed to come out, and the container here, this container here and the water here are going to fall together at the same rate. Therefore, the water will be unable to come out. And if you are a person sitting on this container, if you imagine yourself to be sitting on this container, then you would be falling freely, right? So you would be like the astronaut in the satellite, which is falling freely under gravity. So what you will see is, you will see the water is not going out only, even if there is a hole. So that will make you feel that the weight of the water has become 0. And that is what you make you feel that things are floating in this container. Okay, so have a look into the demonstration. Wow, that was quite fast. So you did not see properly what happened as the container was falling freely. So what I have done, I have slowed down the video and I'll show you again. But try to see carefully the last 3 to 4 seconds. During that time, you will see very nicely that as the container is falling freely, the water is not coming out.